All right, so let's get started. This week we're going to start talking about atoms and elements and all that stuff that you would associate with the chemistry course. Remember last week we kind of introduced sig figs and how we're going to be doing calculations throughout the course, kind of how we handle math in a chemistry course. That was week one. Now we're actually going to start talking about some chemistry, start talking about the periodic table. Okay? So first of all, the atom is sort of, again, the big success of chemistry and why we study chemistry to this day is the idea that early chemists proposed that the world around us was all made up of these tiny little building blocks, atoms, and that turned out to be true, right? And so understanding these tiny little building blocks has helped us better understand the world around us. But what exactly the atom looks like has changed over time quite a bit, okay? So we sort of have this history of progression of what we think an atom looked like back when it was first discovered by John Dalton back in the early 1800s, which is a ridiculously long time ago, right? I mean, it's kind of crazy thinking about the technology that they had there, right? They really just thought that atoms were basically little marbles, little tiny spheres. And that's not a bad approximation for what it is that an atom was. But later on, as technology got better and better, especially around the world wars that broke out in the beginning of the 1900s, sort of really had a big boost in our science technology, they discovered that actually the atom was made up of teeny tiny little particles. Some of them had a positive charge, some of them had a negative charge, and they sort of built upon that theory all the way to where we're going to start our course here, which was with Bohr's planetary model of an atom. At some point, we'll graduate to what is the now modern-day picture of an atom, the quantum mechanical model. But it's a little more complicated, and we're going to kind of simplify things, starting with a little bit simpler of a model here. All right? So let's see if we can't better understand what's going on here in this picture. So first of all, before we can sort of talk about the atom itself, we got to talk about these teeny tiny building blocks that make up an atom, what we call the subatomic particles. Okay? It turns out that an atom is made up of three subatomic particles. We have protons, neutrons, and electrons. All right, so when you're talking about an atom, you're really talking about a collection of these three subatomic particles. All right, and they differ in some major ways here. So first of all, the charge of these particles. They have different masses. And finally, where in the atom they're located. All right, so protons have a positive charge, a charge of +1. And they have a mass of about 1 AMU. Okay, these units, AMU, atomic mass units, that's what they stand for. Okay, we talked about units of mass before, the grams and the pounds. Atoms are so teeny small that using a gram would be like a ridiculously large unit of measure to use. So they have these units that they made up specifically for atoms that are to measure stuff that's really teeny tiny small. Okay? So these special units of AMU we use to talk about the mass of these teeny tiny subatomic particles. Okay? And the proton is located inside what's called the nucleus of the atom. Right? Neutrons are neutral. They have zero charge associated with them. All right, but other than their charge, neutrons are a lot like protons. They also have a mass of about 1 AMU and are located inside the nucleus. All right, and then the last one, electrons. They have a charge of -1. Okay, so they are negatively charged particles. In terms of their mass, they are very much so different than protons and neutrons in that they are extremely, extremely light. They do have some mass associated with them, but it's dramatically less than either the proton or the neutron. So we always say it's about 0 AMU. Truthfully, it's more like 0.0005 AMU. It does have some mass associated with it, but very, very little, right? These are very light little particles. I kind of imagine them as little lightning bolts that are kind of zipping around in that atom. All right? And unlike the protons or the neutrons, they are located outside the nucleus. Okay? So, if we look at our picture of an atom here, we see inside we have this very small, very dense core where all that positive charge lives, the protons and the neutrons, which we call the nucleus, right? So inside our atom here, we have this dense nucleus. And on the outside is where we have all of our electrons that are kind of moving around that central nucleus. Much like how the planets orbit the sun, we have these electrons that are orbiting around that central nucleus sitting in the middle. Okay, so here are our electrons. They're orbiting the nucleus. And remember, all that mass associated with that atom is in those protons and neutrons. So in our little model of our atom here, where is all the mass? On the outer part or the very inner part of our atom? That nucleus, where those protons and neutrons live, right? So all the mass is really associated with that dense core in the middle. The outer portion, most of the atom is actually empty space, made up by where those electrons live. Okay? Of our electrons, we sort of differentiate between those that live in the middle part of the atom versus the very outermost electrons on the outside here. This image is mad at me. All right, so our electrons, we're going to differentiate here. We have two different types. Importantly, and this is a very important vocab word, we have our valence electrons. Those are the outermost electrons in an atom. Okay? And this term outermost means both physically, they are the ones that are located on the outermost layer of the atom, but also the highest energy electrons. And these are really important to understanding the properties of atoms because these are the electrons that actually participate in chemical bonding. Okay, when we start talking about compounds, we start talking about bonds between atoms. Those bonds are going to be made up of these valence electrons here, right? So our valence electrons are the ones that participate in bonding. Okay, and we differentiate these outermost electrons, the high energy ones that participate in bonding, from what we call the core electrons. Those are those innermost electrons in an atom. They are low energy and do not participate in bonding. Okay, so this term valence electron is going to be really important. We're going to hear that over and over again. It turns out that elements that have the same number of valence electrons behave very similarly, even if they have different masses. All right, so we will pay a lot of attention to valence electrons throughout this course. Again, those are the outermost electrons, both physically in an atom, but also the highest energy ones that will participate in chemical bonding. And we're going to see kind of this over and over again. It turns out that the electrons in an atom are really what make it interesting. That nucleus, those protons and their neutrons, they don't really do much. They kind of just sit there. All of the chemistry that happens between atoms and molecules occurs in those electrons. Okay, so now we got what our atom looks like here. So now we're going to take a look at what's going to be a big portion of our course here, the periodic table of elements. Okay, so this is the one that I'm going to use when I create assignments. So this is the one that you guys want to use. We have one up on the board here. It's a good idea to have one printed out because it's helpful to like take little notes on it and stuff like that. All right. So first of all, take a step back. What the heck is the periodic table of elements? This is a summary of all the different types of atoms that we have discovered at this point in the universe. That's what the periodic table is. These are all the different types of atoms that exist out there in the universe. Okay? So let's take a look. We're going to zoom in on one of them here, and we're going to pick apart these tiles on our periodic table. You can see we got a bunch of tiles. They're kind of arranged in this weird little staircase kind of thing. We'll talk about why it's shaped the way that it is. All right, but let's first kind of zoom in and look at one of these tiles and make sure we can understand what's going on here. All right, so we're just going to pick this one here. Okay, at the very top, we have what's called the atomic number. You see each of our tiles on our periodic table have a different atomic number, all right? And that's kind of how they're arranged. Again, there's kind of this weird pattern, but generally speaking, it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, increasing in that atomic number. Okay? We have the name of the elements. So each one of these elements gets their own name. And because we're really lazy in chemistry and all of science, every time we want to talk about this specific element, we don't want to have to write out the name boron. We have then the symbol as a shorthand. Okay? And then down at the bottom here, this number is going to be really important as we move throughout the course. We're not going to do too much with it right off the bat, but we're going to see it's very important. This is what's called the atomic mass, or more specifically, the average atomic mass. All right, and this is kind of the basic information that you get from a periodic table. Some of them are fancier and they have even more information about each element baked into them, but this is kind of the basics of a periodic table here. All right, every element on this periodic table, every tile has a different number, a different name and symbol, and then the average atomic mass. And again, we'll sort of work with those masses quite a bit in the future here. Okay. This atomic number is really important, right? Again, each element has a distinct atomic number. That atomic number corresponds to the number of protons in each atom. Okay, so what makes a boron atom is that if you zoom in and you count how many protons are in there, that particular atom has 5 protons. That's what makes it boron. If it had another proton, it wouldn't be boron anymore. Now all of a sudden it would be carbon with 6 protons, right? So the number of protons is what uniquely distinguishes each of our elements on the periodic table. We have the teeny tiny ones, hydrogen, with only 1 proton, all the way to these humongous ones down here that have, 103 protons, okay? Generally speaking, in this course, we are going to sort of stick with the top few rows on our periodic table here, the top 4 or 5 rows on the periodic table, okay? A lot of these heavier elements down here, They exist maybe in a lab for maybe like a millisecond, so somebody could record that they actually exist, but they're not really stuff that you encounter on your daily life. Okay? There are special ones like uranium that we've figured out that we can mine and create energy out of, but generally speaking, these ones towards the bottom of the periodic table are like the oddballs you've never heard of in your life. All right, and you will see just over and over again, we kind of restrict ourselves to the top part of our periodic table. These are the elements that actually naturally exist in the world around us. All right, especially if you go onto organic chemistry, man, you are hyper-focused on this portion of the periodic table, a very small subset of elements. Cool, all right. So again, we have this table of all the different atoms that we've discovered here on Earth and in the universe. Many of them may be just created in a lab temporarily. Some of them were naturally occurring all around us. And the difference between all these elements is they differ in the number of protons. That's what makes an element a particular element. Okay? So, if I said that I had an atom in my hand, and this atom had 11 protons in it, which element would I be talking about? Yep, absolutely right. So I would just look on my periodic table for element 11. That is sodium. Most of them have pretty normal symbols. There are a few weird ones like Na for sodium or Fe for iron. We'll have this periodic table. This is our periodic table for the course with both the symbol and the name. All right, just sort of make note, potassium's a weird one, that's K. Yeah, normally it's because the element was like discovered in like Germany or something like that, and so the German word for iron is ferrous or something like that. I don't know. Anyways, sometimes the symbols don't exactly match, but yes, we all have both of that information here. All right, cool. So we have our different elements here. So now let's say that I'm talking about a carbon atom. I have this carbon atom in my hand, okay? I could be holding one of a few different what are called isotopes of carbon. Isotopes are atoms with the same number of protons but they differ in the number of neutrons that make up that particular atom. All right, so I can have a carbon atom. If I have a carbon atom, I told you it's carbon. How many protons do I have? 6, right? Necessarily has 6 protons in order to be carbon. If you took one away or added one, it's no longer carbon anymore. All right? So carbon exists in one of 2 different isotopes. There's a carbon with 6 protons and 6 neutrons. Okay, notice my little symbology here for proton with the positive sign, and neutron with the 0 with the not on there, right? Remember what those correspond to. Protons are positively charged, neutrons are neutral. So those are the symbols that we use. Okay, but you can also have carbon that has 6 protons. It's got to have 6 protons in order to be carbon, but actually has 7 neutrons. This would be a pair of what we call carbon isotopes. Okay, same number of protons, but they differ in the number of neutrons. Okay, so if we're talking about a specific atom, we want to differentiate between which one of these 2 isotopes we're talking about. So we have what we call the mass number that we refer to these as. The mass number. All right, and your mass number is defined as the number of protons plus the number of neutrons. Okay, remember all of the mass of that atom, virtually all of the mass of that atom lives in that nucleus with those protons and their neutrons. Right? So the number of protons plus neutrons we call the mass number of that isotope. So let's calculate the mass number for my two isotopes here. For my carbon that has 6 protons and 6 neutrons, what's its mass number? 12 atom together. So we would call this carbon 12. All right, we would be specific about which isotope it is that we're talking about. Not just carbon, but a specific isotope of carbon, carbon 12. And then this one over here with its 6 protons and 7 neutrons, that would be carbon 13. All right, so for a specific isotope, we name it with the name dash mass number. Okay, so carbon 12. That's my isotope name. Okay, and we can also refer to a specific isotope using this symbol. All right, again, we have the shorthand that we use to reference our elements on the periodic table, the symbols. We can do the same thing if we're talking about a specific isotope. All right. So in the same way that the isotope name was name dash mass number, when we do our symbol, we're going to use the symbol for the element. So in the case of carbon, that's that big C. All right, from my periodic table, symbol for carbon is the uppercase C. And since we're referring to a specific element, we put its mass number in the top left corner. So carbon 12. Okay, and honestly, you'll kind of see it just like this sometimes. Other times, they'll sort of put an extra piece of what's kind of redundant information in there, which is to put the atomic number in the bottom left-hand corner. So a 6. It's kind of, I say it's redundant because just by putting that C, you knew I was talking about an element with 6 electrons. But nonetheless, that's the format that our textbook uses. So we'll stick with that. And we'll put the atomic number in that lower left-hand corner. All right. And our last vocab word that we're going to need here is ion. And these are going to be very important. We'll see over and over again. An ion is an atom with a net charge. Okay, so what do I mean by that? Our atom, our subatomic particles that we had. We talked about our protons and our neutrons having all of the mass, but there was this other important property of these subatomic particles that we kind of introduced and haven't talked anything about, and that's the charge of those subatomic particles, right? Every proton that you have in an atom brings with it a +1 charge, and then they're decorated with these electrons on the outside that have a negative charge. So if an atom has the same number of protons that it does electrons, that atom would be neutral. Okay? If it has any more protons than it does electrons, or any more electrons than it does protons, there will be a net charge associated with that atom, and we call those ions. And ions are really important in chemistry. There's a lot of chemistry that happens between ions, between these charged particles. All right? Now, if I'm going to make an ion with sodium here, I'll tell you, sodium forms an ion that has a +1 charge. All right. When we're talking about ions, we write those charges in the top right-hand corner. So this is the charge of my sodium ion. Okay? So, does this sodium have more protons or more electrons? More proton, more of those positively charged protons, okay? But if I'm going to take a sodium atom and form a sodium ion, can I give it an extra proton? What happens when I give it an extra proton? It becomes a different element, right? So these atoms, they can't gain or lose protons, otherwise they change who they are. And in general, just this idea of gaining protons or losing protons isn't really something that's practically possible. They live at the nucleus. The nucleus are kind of like little rocks. They don't really do anything, all right? What you can change is how many electrons you have decorating the outside of that atom, all right? You can take away or add electrons fairly easily. So when sodium forms the sodium ion, it doesn't change the number of protons it has. What it does is it's going to lose an electron. All right? So you go in there and you kick off one of those electrons that are zipping around on the outside of that atom, and it becomes the sodium ion. All right? Now, how I got this +1, y'all are just going to trust me on that for a little bit. We will learn how to look at the periodic table and learn what the charge of an ion is, but we haven't quite gotten there yet. So for right now, you're just going to trust me that these are the charges that these elements form. Okay? Likewise, I can take another one, fluorine, on the other side of my periodic table here. Fluorine will form ions that have a -1 charge. So if it has this -1 charge associated with it, does it have more protons or more electrons? More electrons. And importantly, you're not going to then take away a proton because you can't change the number of protons. In order for fluorine to become this ion, it's going to gain an electron. It steals it from one of the other atoms to become this fluorine ion. Okay? So, ions, they're atoms with a net charge. So what does that mean? By either gaining or losing electrons. Okay. All right, so now that we've discussed about these isotopes, their mass numbers, their charges, all that jazz, let's see if we can't fill in this table here about some of these elements. Okay, so we want the name, the symbol, the number of protons, neutrons, and electrons, and then lastly the charge. Okay, so we're going to fill in some of this information, and then you guys are going to fill in what's missing here. So I am talking about sodium 23. Okay, actually we can put in another category here for mass number just to keep track of that as well. All right, and if I have this sodium 23 atom with a net charge of 0, I want you to take a second and to fill in the rest of this information here. How many protons, electrons, and neutrons does this particular atom have? What's its mass number? And then lastly, how do I summarize that in its symbol? right, so because I told you that this was sodium, which one of these boxes can we fill in right off the bat here? The number of protons. Because if I'm telling you it's sodium, I'm uniquely talking about this atom right here with its 11 protons. All right, and then I didn't just tell you sodium, I told you a specific isotope, sodium-23. So what is that 23 telling us? The mass number, right? That's what we put on our name for a specific isotope. So if it's sodium-23, I know my mass number is 23. Okay? Now, I told you that we had a neutral sodium atom, right? I'm not talking about a sodium ion. I'm talking about a neutral sodium atom with a net charge of 0. So if it's got a net charge of 0 and it's got 11 protons, how many electrons does it have? 11. They got to be balanced, right? That's why I don't have any net charge. Boom. Okay. We can do our symbol here based on this information. Sodium's symbol is Na. We're talking about sodium-23, so I put that mass number in the top left corner and the atomic number of 11 in the bottom left corner. So then we have one more box here. The number of neutrons. How am I going to figure out the number of neutrons based on this information? Using my mass number and the number of protons, right? Because let's remember, our mass number is protons plus neutrons. I know my mass number is 23. I know my number of protons is 11 because I'm talking about sodium. So the only thing that I'm missing from this equation here is that number of neutrons. So I can take the 23, subtract the 11, and I would get 12. Okay? All right, so let's play this game again here, but I'm going to give you some different pieces of information. I'm going to tell you that this next one has 17 protons, a charge of -1, and its mass number is 35. And I want you to see if you can't fill in the rest of this information here. All right, so I told you that this atom that I'm holding in my hand has 17 protons. So which element am I talking about? Chlorine, right? Element 17 here. When we're starting off in this chemistry course, everything is going to sound like a foreign language off of the periodic table. And then you'll see that we talk about these same elements over and over and over again, and it'll just start to sound weird. So I know that everything kind of like looks weird on the page. It sounds weird when we say it out loud. Getting used to the language of chemistry is part of being in the course, all right? But yes, this one is chlorine. If you have a spa or a pool, you would have heard of this element before. We use it as a sort of antimicrobial. Turns out that bacteria and yeast and stuff don't like this element very much. All right? And not only can we say it's chlorine, but we can talk about a specific isotope here, chlorine 35. Name dash mass number. So the symbol for chlorine is that Cl. Again, we're going to put the mass number at the top and the atomic number down at the bottom. Okay. How am I going to figure out how many neutrons are in this chlorine atom? Yeah, so I know my mass number. I know that this is 17 protons. So again, the only variable that I'm missing here is my number of neutrons. Subtracting 17 from 35 will leave me with 18. Okay. Now, this isn't just a chlorine atom, but I can say even more specifically that I'm talking about a chlorine ion here. Okay. So that -1 charge is important, first of all, in my symbol. I got to go back and fix my symbol here because we need that charge in the upper left-hand corner. Nope, upper right-hand corner. Okay. And then lastly, I need to fill in my number of electrons here. Okay, so first of all, in terms of charge, we can think about this as a math equation as well. Our net charge is equal to the number of protons minus the number of electrons. All right? And if you like thinking about things as a math equation, great. You can think about this, it'll work every single time. All right? One thing that I sort of think helps making a stupid mistake is instead to just take a step back, look at this net charge of -1 and ask yourself, should there be more electrons or more protons? More electrons if I have this -1 charge, right? So we don't have to think about it as a math equation. You can, but it's almost easier to just look and say, should I have more protons or more electrons here? A -1 charge means I should have 1 extra electron, so that would be 18 electrons and 17 protons. Okay? Again, we can't change this number of protons here because then it stops being chlorine. All we can do is add or remove electrons from that atom. All right? So this ion here has 1 extra electron. Okay? And just real quick about ion symbology, that just because you'll see it a few different ways. Okay? You can do sort of like you would expect in math, where you have the sign out front and then the number. The other thing you'll see that's kind of specific to chemistry is the number and then the sign. Okay? And then specifically, if it's a plus or minus, they get lazy, and sometimes you'll just see the minus sign. All right? I myself, when I was in school, I did a lot of math and physics, and this like normal charge symbol then the value, or rather sign then the value, this is the one that I kind of tend to default to, although you'll see me write it both ways, no rhyme or reason. Importantly, this is what you're going to need for your homework. Your homework only accepts it with that sign then value. Okay? All right, let's do one more. Again, I'm going to give you some of this information. You're going to fill in what's missing here. Let's replace this one. All right, so I'm not going to give you the name, the symbol, or the number of protons. I'm going to tell you that this isotope that I'm holding in my hand has 20 neutrons, has a charge of +2, and a mass number of 40. All right, so see if you can't fill in, figure out who it is that we're talking about here. All right, so what element am I talking about here? Calcium. And how did I know that it was calcium here? All right, I had to first figure out my number of protons. What I had was my mass number was 40. I didn't know my number of protons, but I do know that I had 20 neutrons, right? So using that mass number and the number of neutrons in that isotope, you can subtract and find that you have 20 protons, which then points to element 20 on our periodic table here, calcium. And specifically calcium 40. Okay. If we're going to do our symbol, we're going to use Ca for calcium. We're going to put our mass number in the top corner and the atomic number in the bottom corner. And then what do I need lastly to finish off this symbol? The charge. Charge in the top left, top right. Okay. And then lastly, I got to figure out how many of those electrons I have on the outside of this ion here. I have a +2 charge, so should I have more protons or electrons? More protons. I should have 2 more protons than I do electrons, so 18. And again, you can use this equation here. You'll always get the correct number, but it's a little bit easier, I think, to not think about it as a math problem. Cool. All right, so we're going to talk a lot about these different elements here. Let me just make some notes on this table. All right, and the properties of these elements. Okay, so first of all, why is the periodic table arranged that it is, right? It's like this little staircase thing. Why isn't it just like one solid block? Okay, so it turns out, and honestly, it was really impressive. This Russian dude created this periodic table and organized it this way. And we have like so much better of an understanding now of these elements that he kind of just crushed it right off the bat. But his logic was that he was going to group elements that behave the same into columns. So it turns out that depending on where you live on the periodic table, all elements within a given column have very similar chemical properties. And we'll talk about what exactly I mean by chemical properties throughout the course. But that's why it's organized into this little staircasey thing instead of just being one solid block, is they put every element that behaves the same into one column. Okay? So we have special names for these columns then. All right? This first row here, or rather this first column here, we call the alkali metals. And again, everybody in that alkali metal category behaves very similar. Okay. Our next column is the alkaline earth metals. This middle block here, we're going to group all these together. These are what are called the transition metals. All right. Jumping all the way to the other side of our periodic table here, this very last column. These are what are called the noble gases. Right? They get this name because they are all gases, but they also are very inert compounds, meaning they don't form chemical bonds with other elements. Right? So we're going to talk a lot about compounds when elements bind to one another. It turns out that everything in this row here are kind of snobby, and they don't like forming bonds with any other elements. You always find them only by themselves, isolated out in nature. Okay? The next row over with fluorine, chlorine, bromine. These are the halogens. Okay, and truthfully, some of these other rows, our columns have names, like this one's the chalcogens, but we don't need to know that. Those are pretty specialized here. So these are the big 5 categories that we need to know. Okay, we have our alkali and alkaline metals at the very beginning. We have our transition metals in the middle. Over on the other side, the very far column, are our noble gases. And then lastly, our halogens. All right? And we'll sort of pick up there and talk about ions and stuff next class. It turns out that all halogens form ions with a -1 charge, for example. All right? So we'll figure out based on where something lives in the periodic table what its charge is. So real quick, our SI leader wants to say a few words regarding the schedule change. Go for it.